Okay, welcome back to Physics for Students, everyone. And today we are absolutely thrilled to have a leading expert in astrophysics and precision astronomy joining with us directly from Madrid, Spain. Dr. Julia Campa is a professor and researcher who dedicates her work to unraveling the mysteries of the universe. Dr. Campa's research journey is truly fascinating. She delved deep into the secrets of galaxy clusters, using them as powerful tools to understand the expansion of our universe. Her impressive career also includes a stint as a visiting scientist at the prestigious Fermi National Accelerator Laboratory, working on the Dark Energy Camera project. So before we dive into the wonders of astrophysics, I want to extend a big thank to Dr. Julia and to all our valued subscribers on the Physics for Students channel. Your support allows us to bring incredible guests like Dr. Campa to us. Dr. Julia Campa, a warm welcome from the entire family of Physics for Students.
Thank you. Thank you for inviting me.
Absolutely, you're welcome. So already we got few people who are waiting, and Richard Nolling is telling that thank you for organizing this, Dr. Campa and Shaunak. Greetings from Australia. So Richard, if you're watching, same greetings from all of us. So I will just set the target how we will go today. Dr. Julia has got a presentation, and she would be showing the presentation in order to explain certain things which she already has got a store. And then we will move on to answer all your questions and certain important and interesting things about precision astronomy and astrophysics. And over to you, Dr. Julia.
Yes, I collect some slides I think they are not in a good order, but just some pieces I thought they were important and they were significant to understand my work, what I've been doing. And if I start with this is the first slide. It's about a question you can ask me is why I've started to combine astronomy with silicon devices. So I started working in astrophysics in 2005. I started working with the dark energy camera. So this camera was populated with a new kind of silicon devices called CCDs that were built in US in the LVNL lab. These charged-coupled devices are used in a wide range of astronomical applications to obtain images for different objects, astronomical objects like galaxy, cluster of galaxy or supernovae, and they are used because you can obtain a very high resolution and very low noise. These new CCDs are used, the properties that these kind of CCDs are the best ones for study distant galaxies because they have high quantum efficiency in the red and near infrared. So thanks to these new detectors, you will be able to observe a large number of much larger of objects and a larger volume of our visible universe than with all ones. So, but I wanted to tell you something before to talk about devices. So I started to work with this new camera called darkenergysurveycamera, and the goal of this project was to study the dark energy and also the dark matter. But we want to know why the universe is expanding. So we want to try to discover what is the dark energy and why the universe is expanding. Here in this picture, it's in Spanish, but I am explaining you in English. So this is a Big Bang, and then you can see how the scale of the universe is changing because the galaxies are expanding. So as farther as they are in time, as in time you can see that nowadays they are the distance are greater than in the beginning of the universe. So so if you know about the Hubble Law, what is the Hubble Law? Hubble discovered that the velocity of the galaxies are greater when they are in a longer distance. So as far they are, the velocity is higher. So if we want to test this law to study the universe, we need to measure the velocity. And how we measure the velocity? We measure the redshift. The redshift is an effect that is due because of the galaxies are moving. They are moving away each other. So if they are they are not approaching us. If they are approaching us, you can see a blue sieve. The wavelength is less than if they are moving away. So if they are moving away, you can see a red sieve, if not a blue sieve. So this is it's the same effect when you hear a train that is getting away from us or is approaching to us. You can see the sound, how change the sound as a function of the movement. But also this happened with the light. This is the same effect with light, and also with the gravity. So if you think in Albert Einstein and the gravity, the relativity theory, instead of the galaxies are moving, what is moving apart is the space-time. So due to the space-time variation, you will be able to measure a redshift of the light. So our goal is to measure the redshift of very distant galaxies to understand, to measure the velocity. But how we measure it? We need we have to build an instrument, and we are going to use these charged couple devices called CCDs. We can use the spectroscopy of the light. This is a light source. If you have a light source, then that goes through the slit, and then it gets diffracted, and the light is decomposed in a spectrum. So depending on the light source, you can measure the properties of the galaxy, and comparing if you have like a calibration method of the light, you can see how the wavelength is moved, and you can measure the redshift comparing with a standard. So, but this technique is very expensive because you have to move your camera in all the objects you see in the sky. So the other thing that we can do is make a photograph instead of a spectroscopy of the sky. We can make photographs. So in both experiments, both kinds of experiments or instrumentation, we are going to use. Sorry.
Just to interrupt you, Dr. Campa. So the thing is that this is what precision astronomy exactly does. That it measures the redshift so that the structure of the galaxies are much better, are measured in a better way.
Yeah. So this is yes. one of the things we want is precision with redshift. Have a very good precision with redshift, and use the devices that can measure the light with longer wavelengths. Mm-hmm. So this new kind of CCDs that we're using this camera DECam that I want to show you later. We knew a new kind of CCD with can measure longer wavelengths. So there are other systematics that we have when you take an image of the sky that I will show you later. That you have to. You don't measure the redshift. You can measure the ellipticity of the galaxies, and as better you have your CCD, your image will be more realistic, and you can measure with precision the ellipticity of the galaxies. Okay, so now we want to measure the redshift, and this is some picture of the camera. I was working in the camera. Is in Chile. It's already installed, and the survey has already finished. And now we are making studies all the images of the survey. The camera has 62 CCDs, and it covers 5,000 degrees between redshift 0.1 and 1.2. It's a great collaboration in different countries, in US, Brazil, UK, and Chile, and also Spain. So here is the camera with 62 CCD. This is how the images are. Yeah.
I just have one question, Doctor. That this camera that you are building in, I mean to say, it might sound a little bit foolish, but do you put this camera on a telescope, or
yes.
I mean, how do you measure?
Sorry, can you repeat?
How do they measure? I mean to say, this camera is finally put up in a telescope, or how it is measured?
How is measured?
I mean to say, how do you take the photographs of those stellar images? Yeah.
How I take the photograph?
Yeah.
So if let me see, if you have a bigger picture, I'm gonna. So
skip this part as of now. You proceed in the usual way. We will take up questions also. Yeah.
You know, I want to show you a picture of the. Can you see this this picture?
You need to share, yeah.
Yeah,
present, and then you go to
share screen. Share screen. Here. Now, I think here you can see. I think you can see now these new slides.
Yeah.
So this is a telescope. Okay. So imagine this is the optical lens. So the lights come from the right. Can you see my pointer? From here to here. So the light goes through the lens, and here, this is the CCD readout. This is the filters. You select the filters. You put different filters to select which wavelength you want to see. And the imager is here. It's in the back. So
Yes.
after the light, yeah. So here is the camera, and here is the dome, the building where is the telescope,
Right.
and the dome is open, and then through a control room, you choose the telescope is moving and covering an area you want to make the photograph, the pictures.
Right. Okay.
This was your question? I don't know.
Yeah, absolutely. I got it. You can go ahead with the rest of the. Yeah.
Yeah. Okay. So
Sorry.
now here. So here, if you want to make a big survey, every hexagon is a picture. So you have to do a lot of pictures to cover all the sky. So this is a plane. This is not important. It's just details of the camera.
Yeah.
Yeah. And now I want to. I think it's since I've been working with these devices many times in a lot of there is a lot of effort with to develop these devices. I want to explain you how they work. So this is so imagine that the rain are photons. So the rain fall into these buckets, and imagine on the right there is a CCD. So a CCD is a semiconductor. So imagine that the photon is the rain that fall into a bucket, and the water is the charge. So the photons strikes the semiconductor, and due to the electron photoelectric effect, if you remember Albert Einstein effect, the photon is converted in an electron. Okay. So now the water are our electrons. So rains fall and convert in electrons due to the photoelectric effect, and then you move these electrons in through these buckets in one direction, in this direction. So there are many files, many rows, and you move the water between these buckets. So because they are electrons, if you want to move the electrons, you need potential, like potential wells. So you move the charge using potentials, and then they reach the readout register. So you move every row, and then when you arrive to the readout register, you move all the charge in one row.
Right.
Okay, I don't know.
No, I got your point. This is quite clear. Yeah.
Yeah, I think it's clear. So here I can also share an animation.
No, that's fine. Yeah.
Okay, so this is how you move this the charts. So there are many types of CCD. So these outstanding CCD that we use they are outstanding because they are thicker than the CCD that were used conventionally in other instruments, and they are thicker. So and they are illuminated from the back to avoid reflection from the gates. So this is a CCD, the light comes from the back, and this is the semiconductor area. Then the light is converted to electrons, and here are the electrons that move the charge. So these CCDs are thicker than than the ones that were used in astronomy. And the result is that the quantum efficiency in the infrared is increases, and you can see objects that are very far away. So this is why the observation length of the light increase with the wavelength. So if you make your device thicker, you can measure longer wavelengths. So this is okay. So this is the red line is the quantum efficiency of the CCD of the DECam camera, and the blue one is the conventional ones. So we have improved our efficiency by almost I think it's double or 60-70%. So it's a lot. So these are the George Smith and William Boyle. They win the Nobel Prize because of the CCD developed.
Right.
So there are other effects. Remember about the redshift effect to measure the velocity, but there are other effects that are very interesting. Highly interesting in cosmology. It's one of the effects is the weak lensing effect. So the weak lensing effect is due to you can see how an image is distorted or lensed because there is some foreground galaxy and the light is blended due to a gravity. So cosmologists are very interested in this kind of objects to study the dark matter, to discover what is it. So you need a device, a perfect device. So imagine that you put a telescope on the sky, and there is radiation. So if there is no radiation, you will see an object like this, like in the one is in the middle. Mm-hmm. But if there are protons from the sun that are hitting my device, they will introduce some traps or some defects that distorted your image, and you can see this trail on the right due to the protons of the sky, of the sun. So when you develop your CCD, you have also to develop your electronics and try to read all the charts in a way that can avoid this kind of effects due to the protons of the sun. So the most easy is to make pictures in the ground, but it's better if you do if it will improve your knowledge in the sky, in the space, because you avoid you don't have the atmosphere and you can see better all the objects. So if you ask me an important discovery made with CCDs, the Hubble telescope was launched in the 90s, in 1990, and it has been the most important instrument of the last century and the early 21st century. So there has been spectacular images sending back to the Earth, observers, and we can appreciate our universe using these images. So here there is a link. Sorry.
Okay. So can I have a few questions to you now?
Yeah.
Okay, first of all, Sudeshna Ganguly, I think
Oh,
you know her, who referred your
yes.
name. She is telling, great to see you, Julia. And thank to Sudeshna ma'am, because she's the one from Fermilab who referred. So thank you,
Thank
Sudeshna
you.
ma'am.
So,
Dr. Ganguly, thanks a lot because she's the one. Okay, so with your permission, Doctor, can I just put off this presentation? I mean to say, are there certain significant things more to show, or we can go to the questions part?
yeah, I think we can go to the questions. Now
Okay,
you know what is a CCD, and I can continue all my life.
okay, fine, thank you. Okay, so my first question would be that for you, what actually sparked your interest in combining astronomy with silicon device? I mean to say, why? How do you find that interest?
How is when you are a scientist, uh, first you want to know why and how the things happen. So that if you are looking to in the sky, you want to know the theory on how the galaxy form and the physics of the universe. But then you realize that you need to build instrumentation, very good instrumentation. If you don't have the devices, you will not be able to understand the theory you want to test. So it's more. I was very interested because you can do a lot of science. So once you know what you want to measure, so if I want to measure the weak lensing effect or how the galaxies are moving apart, you need the best precision instruments
Right,
to
absolutely.
see.
So that was interesting. So I mean to say, your family, your parents, your father, or anybody is already or was already into astronomy or astrophysics. That
No, no, I was the only one in my family. The, yeah, they wanted. So they told me, if you are so intelligent, why you don't do it? You work like in a company as a director or something. And I said, no, I want to study physics. But my father was working in a company that built cameras, photo cameras, and I remember that he loves the cameras and all these uh, instruments. So I think this one thing that
so your father's interest in camera actually
yeah,
got something related to that. Okay.
yes, yes.
Okay. So I have one question for you, Dr. Julia. I mean to say, you can give me a very simple example. How do astronomers, measure the age of stars? Can you give me a simple example? I mean to say, mathematically or analysis-wise, how do we progress? For example, we have a star out there, anything, X, Y, Z, or something, and then we want to measure the age of the stars. How do we go about? How do we start doing that?
So you need you need to know the distance. If you once you know the distance, you measuring the redshift, then you will know the age of the star. It's how long takes the star to reach the Earth.
Okay.
But the age of the star depends on when is the start point of the universe.
Mhm.
So it's not an easy question.
So basically, you measure the first is the redshift, and
Yeah,
based
it's
on that,
relative.
you go about that. And as
And
you told, that, yeah,
on the it's depending of the component. So a star is every star has a there is many types of stars, and every star has a type of has a life. So there are stars that are that lives longer than others. So there are many factors to understand to measure the age of a star. So it's depending of the component they have. With the spectrography, you can measure which component they have and the distance between the star and the Earth, and then you make a it's a likelihood. There is a how likely. So it's not so precision like for humans, but it's yeah.
Okay. Okay. Well, I would like to ask you, Doctor, one question is that these exoplanets that we call, what are actually exoplanets and why do astronomers find them very interesting? What actually is so special about exoplanets?
Yeah, so in this, we are developing a new. So, like 10 years ago, we start to discover exoplanets, and then because of the new technology to discover them, we start with 110 like 100 of them, but now we have 1,000, and there are so many planets as not like a star, but there are 1,000, and is growing. The velocity of discovering exoplanet is growing a lot. So the new technology, there are new instrumentation and new techniques that allow us to search for new exoplanets. So in science there are like trends. So we have now the trend in exoplanets, and also in cosmology now it's not so fashion. But the thing is that we are discovering many planets. So even we have a new technology. Can I show you my slides? Yeah. So if stop the screen. No, it's here. Here.
You want to show this one? No.
No. This one. No. Stop the screen. Here.
Yeah. This one?
Yeah. Yes. No. So now this is an image of Jupiter. It's not with a CCD. But so there are new silicon devices that allows you to measure the light with very low noise. So there is a new generation of CCD that is going to make a big step in the discovering of new things for new objects, for cosmology, and also for if we follow doing a lot of effort, we can use them for exoplanet search, because you have almost devices with zero noise. So the improvement of these detectors will allow you to put this kind of new devices in coronagraphs that are instrumentation to search for exoplanets.
Okay.
So another thing that is important is in this new era of exoplanet is because we are looking for another planets to live in case we don't have in the future.
Yes, we are looking for colonization in Mars, and Elon Musk is.
No, I don't. I don't think we should go to Mars or on any other planets, but we are looking for any other habitable planets because we are humans, so we need something to
Yeah.
some application of this search, and in case you can also find new forms of life. But the technology, we are developing technology that's these new CCDs to see planets that the light is very faint. So if you have a zero noise, you can see almost in the dark. So it's like put a camera in the dark.
Okay. We have a question coming up from Vishnu Prasad Tripathi. I'm just removing, with your permission, this presentation so that.
Okay.
The first thing is, what is the future of astronomy, and what is the relation between astronomy and theory of everything?
Theory of everything is the field or the unified theory?
I think yes, you are right, Dr. Julia. So he is trying to understand that unified theory of everything, how does it has any relation at all with astronomy? I think the first question is more pertinent. What is the future of astronomy?
Oh, yes. So now, as you tell us before, the future of the astronomy is now in the exoplanet search. Okay. So the scientists are going to build a new kind of instrumentation. We are developing new kind of instrumentation to launch to the space and search for exoplanets. But also now here, if I want to show my slides, I don't know how to do it. You are in the show here. So I want to show you some of there are many projects. Here, this is Cerro Tololo. So this Cerro Tololo is where the DECam camera was, and this survey is done. Still, you can do observation, but there are the new generation. There is another instrument that we are building now. Is the LSST. That is a huge camera. If the DS has 520 megapixel, this has I think it's 3 to. I have a link here. So it's around 3,200. So it's huge. It's a huge camera, and it's 6 times. If you make a photo, it's 6 times the moon. So in 2025, this instrument will be built, and you can do a big survey of all the galaxies and study how the universe is expanding, study the Milky Way, and yes. So the future, and in our moment, for ground astronomy, the future is here in the LSST. But if you want to, can you put it again? Yeah. Yes. So the future is in the Vera Rubin Observatory with this huge camera. There are also other type of detectors that they are going to make a big step in. I don't know if I'm going to show you. There are new detectors that we are developing to watch the sky in optical and near infrared, like kits that are resonators. You cannot take pictures with them, but you can look for signals very fast and measure one single photon very fast with this new technology. So instead of making photos, you look for some points.
Great.
Yes.
So Brishnu Prasad, you got the answer to your question. With your permission, I'm just putting up this slide. Whenever you need, you can let me know so that we can take some more questions. I would now keep it open that if there are subscribers and who wants to ask the question. Okay, we have got the question. I think this is something which you can, this is quite common. What is the difference between astrophysics and cosmology?
Astrophysics study the objects and the physics of the object of the sky. So you study how a galaxy is formed, how you build instrumentation to make pictures of the sky, and it includes astronomy, the position of the object, and the geometry of the universe. But in cosmology is not only how the galaxies form, and it's more deep in theoretical physics. So it's a study how the universe is formed, what are the components of the universe, and what is the story of our universe. So it's also so you can study cosmology without astrophysics if you want to know what are the components of the universe. You don't need the sky. You can study cosmology in an accelerator, creating new particles, looking for the Higgs. But I would prefer to study cosmology looking at what we have in the sky. And
cosmology, I would say, is much a bigger area. Astrophysics particularly deals with the movement of stellar areas with the help of physics. Yeah. So we have got another question. Dr. Rajkumar Mukherjee is asking, what type of spectroscopy has a vital role on astronomy?
What type of spectroscopy? For example, for cosmology, since I'm working in cosmology, I know more about cosmology that spectroscopy for measuring the redshift. So you have a photo of a quasar of a galaxy, and you measure the distance to this galaxy. So now with big surveys, the spectroscopy of big areas has a vital role in astronomy, because we are developing a lot of technology to make big surveys and so you combine the photometry, the picture, with the wavelengths of the object.
Yeah. Okay. Thank you. Thank you for answering this question. So I know that it is not possible for a naked eye to have a vision of what is a star and what is a planet. But say, for example, for a person like me, those people who are not into astronomy. So we put up a telescope and we try to see, and we first try to find out that object which is going on. So how would I identify? What are the characteristics of a star and a planet? How would we distinguish?
Yeah. So it's how the how is the light from a planet and how is the light from a star. So the planets are closer than a star. So if the light, in both cases, the light pass through the atmosphere. So if the stars are farther than a planet, you will see that the light is distorted more than in a planet. So this distortion is like this blink is called in English blink. Yeah. So it's an intermittent light, and so it's twinkle. So you can see like light. The planet is a continuous light, but stars stop like make flashes.
Okay.
Twinkle.
Right.
So it's because if they are close, the distortion is not so high that if they are far away. The distortion of the atmosphere, the reflection of the light in the refraction of the light in the atmosphere.
Okay. My next question to you, Doctor, is that what are some of the challenges that you I'm so sorry. What are some of the challenges that you face when you're designing silicon devices for the astronomical applications?
Now, the core of our study is in the readout speed. So it's electronics. Now we are with the electronics, trying to read the picture in a faster way. So one point is controlling the readout of the device, but other things that are very important are vital is it's depending of the wavelength you want to measure. For example, normally you use silicon detectors, but we are thinking in using, instead of silicon, germanium, because the germanium has a band gap in the semiconductors. The semiconductor has a band gap, and in germanium is smaller. So with a smaller band gap, you can reach higher wavelengths. So, but the problem with the germanium is the noise. So we are trying to develop like a skipper CCDs with germanium to reach near infrared. So you can reach, so you can take pictures in the infrared in another wavelengths.
Okay.
So, okay. And there are many issues you can find. Also, the material to avoid the reflection of the light in the CCD. You prove different materials to avoid the reflection, the coatings, and yeah.
Okay, we have another question from Akash. He's saying, "Thank you so much, ma'am. Just another question: are white holes really there in the universe? If yes, then
oh my God,
violate the law of entropy."
I don't know. What is I don't know what is a white hole. Sorry.
Yeah, I think that Akash, you can ask this question later to somebody else, because Dr. Julia deals with a different subject. Black holes and white holes are something I would say that, yeah. So anyway, so I would like to ask you that for those who are interested in pursuing this career in the field, what is the best, or what is the advice that you would like to give to them?
Okay. So my advice is try to join a group that is strong and has a lot of funding
Mhm.
to start your research. So like they work in the state of the art of some topic, and also that you like. So if you don't like it, you don't go inside. So you have to love what you are doing. And there are for astrophysics there are many groups that are working. It's a very wide area. So every topic in astrophysics has a different. It's almost like a career. So for me, you have to work to work very hard and be very meticulous and also make a wide network of people working. So it's not only your work and also the people where and how you collaborate with people. I think is very important to work in a team and in a collaboration to share the knowledge. So now I think it's an issue that is an issue is that there is a lot of competition between groups. So for that it's important you be in a good group with fundings and doing what you like.
Absolutely. We got a question from your friend and colleague, Dr. Sudeshna Ganguly, and she is asking, how do you calibrate astrophysical detectors to ensure accurate measurements?
Yeah, we test every detector of that will be placed in our camera in a lab, in a optical lab. So we place our detector in a vacuum chamber and we cool it and do many tests with light and without light to measure the noise, the linear behavior, if the light changes in a linear way when increase the exposure time, the transfer efficiency. We measure the efficiency in different wavelengths.
Okay.
We have to, and the scientists give us some requirements that they need it, and we have to test if they follow these requirements.
Absolutely. Thank you. Thank you for asking this question, Dr. Ganguly, and thank you, Dr. Julia, for answering this. I would have one last question for you. Now, if I am, observing certain things over a telescope, now, how do we measure, or what are the characteristics that you have rightly explained about the stars and the planet, the deflection of the light? Now, in case that we encounter a galaxy, we see a galaxy. So, what are the characteristics, or how do we identify that this is a galaxy and not anything else?
So it's we have already a previous map. Sometimes you have a previous map that someone has made before and you go directly to this object. So you know what you are looking for sometimes because you have the position of the object. But if you don't have that and you are like exploring the universe, you have a picture. So if you have a picture of a galaxy with this new kind of cameras, you can see that it's a galaxy because of the shape of the picture. And also with spectroscopy, you can see what it's made of. So and you also know the distance of the objects. So depending, So it's in pictures, you know what you are looking for. So it's depending. So there are many types of objects. So if you want to study galaxies, you need more exposure time than if you are looking for for other kind of objects that their life is shorter. So it's the quantity of light you are measuring, how much is your exposure time, the shape of the object. So there are many different techniques to detect the objects by machine learning. So it's the shape, the size, the light you are measuring.
Right, I got your point.
Yeah.
So my last question would be those who are the students who wants to take up physics and astronomy, especially in the area that they want to go for an observational study. What would you suggest to them? What would be their path? What would be the initial steps? And what are the areas that a student should be aware about in order to take this as a career?
To study before, or
Yeah, I mean to say, what are the steps that we should take? Mathematics or data science? I mean to say the cosmology part, the theoretical part. What are the
if you want to do observation, you need now you need a lot of data science, because now for detecting objects you need a lot of machine learning and these new techniques to detect objects. And also you need, but you also need like programming, a lot of programming skills if you want to be more theoretical and do simulations of your sky, of your theories, and also when you study astrophysics, you have to study many signatures. It's I think it's hard. It's not only one course. There are many courses, and it's depending if you have theories. You need more mathematics and more
what is the
physics.
level of mathematics that you would suggest to take them?
It's very high level of mathematics. You need to know. It's more physics, theoretical physics that include mathematics, like particle physics. For cosmology, you need particle physics, like relativistic physics, mechanical physics. So you need a lot of differential equations, understand the differential equations, and mechanical quantum theory and classic theory for cosmology. And but if you are more interested in astrophysics, it's not so hard, but also you need to study many subjects like electromagnetism, also mechanical and relativistic physics. But no particle physics is not so useful for astrophysics. It's useful, but if you are not a cosmology, you don't have to do it.
We have already Dr. Ganguly who's watching, as she is a great scientist in terms of particle physics.
Yeah, but it's So yes, because in astrophysics we study all the things that come from the sky, and you have to study particles, all the things that are in the sky. So as much as you know, you improve your knowledge. So I think you have to study astrophysics. I think is everything, and cosmology. It includes everything.
It includes everything. So thank you. It's almost an hour, Doctor. So I hope you enjoyed today's conversation.
Yes, hello. Thank you.
It was a lot of learning from our side also. So, from me and from all the subscribers who are watching this live podcast, I would immensely thank you, and I would like to wish you all the best in terms of your future endeavors, future, prospects, and careers that you are taking up. So you are already doing into precision astronomy. So maybe you have great projects which are lying up in the future, and
Yeah. Yes. Thank you.
and you're already teaching, I think, in a university in Spain.
Yeah, I finished my project in the university, and now I'm looking for new opportunities in this in instrumentation for with the skipper CCDs, and also in I will continue teaching next year, I hope.
So what is the
I
subject?
love teaching because you learn a lot teaching.
Yes. So you teach primarily to which level of students? The grad,
I
undergrad?
Yeah, I teach graduate. The last year I've been teaching bachelor degree students. I teach them astrophysics and particle and nuclear physics, and also quantum physics. So are the yeah. But like 2 years ago, I was a master thesis director. So no, undergraduate doctoral students. But it's another way of teaching. Yeah, you teaching, you work together more than teaching. Yeah.
Students must be very happy to get a teacher like you.
Yeah.
I mean,
Yeah, I think in the last course with the astrophysics, we have a lot of fun in our course. I think they learn a lot because
so along with the teaching, do you take the students to observe the sky through telescopes or etc., or is it only the classroom teaching that you do?
In the last year we use a software that allows you to look for an object and study the astronomy position and calculate some quantities of an object. So in our university we don't have a dome, but we are planning to do one to go out and observe, because I think we need more funding and instrument. We need no, it's not more funding. We need more develop a dome and a telescope to start with other students, and so we are planning to build an spectrographs also, a small spectrographs, not a big one.
Okay.
And yeah, and a telescope to make some practice for the near, no so far objects like Jupiter of the moon that you can see almost by eye or with a telescope.
Right. Okay. So
Yeah.
thank you, Doctor. Thank you very much for coming. Deeply privileged and honored to get you for almost about an hour. So thanks a lot. And from Physics for Students, I would sign off, wishing you all the best and thanking all the subscribers who has asked beautiful questions, including Dr. Ganguly, who is joined, and wishing you all the best. Thank you very much.
Okay. Thank you.
Thank you. Bye.
Bye.